Now we'll start with vector spaces. Vector spaces seem complicated on the surface, but these are actually very familiar. Okay. For example, the plane that you're used to, R2, is a vector space, and so's three-dimensional space, or any dimensional space. That's what this R to the n means. Okay. A vector space really is a space of vectors where you can add any two vectors in there, and then you get a third vector in the space. That's what these are saying here, right here, these properties. If these are two vectors, you add them, it's also a vector in the same space. And the rest of the properties are kind of natural things that you're already used to, like this commutativity of addition, that you can change the order in which you add things. This is called associativity of addition. Again, you can choose, if you have three vectors that you're adding together, you can add the first two together, or you can you can add the first two together first and then add the third one, or you can add the last two together first and then add the first one. Okay, so you can change the order in which you do things. There's a zero vector, the origin that you're used to. And when I add it to any vector, I don't change the vector. Okay, I can also come up with a negative vector, so a vector pointing in the negative direction. I add this to the original vector, I'm going to get the zero vector. Okay, I can also scale the vectors, so I can make them longer or shorter. Okay, I can scale by 1, which leaves the length unchanged, leaves the vector unchanged. And I can also do different things with scalar multiplication. For example, I can distribute a scalar into the sum of vectors like that. Okay, so these are the kind of just a formalization of something that you know already. Okay, really, when you're thinking about these vector spaces, you can have the picture of two-dimensional space in your mind and how vectors work in two-dimensional space, and that's more or less good enough. That will keep you going throughout this course. Now, when we have a vector space, we want to be able to describe the vectors in that space. Okay, this is like your familiar Cartesian coordinates. We want to be able to do that in any vector space. And in order to do that, we're going to look at span and linear independence. Okay, so with span, we're just looking at what's called all linear combinations of a set of vectors, and then we see what space this traces out. Okay, and here's a linear combination. We just have a bunch of vectors like v, u, and w, and these constants a, b, and c, and when we combine them in this way, that's called a linear combination. Okay, so let's look at an example here. Let's take the vector 1, 2. Actually, and what I'll do is drop down to Desmos. Oh, I'm going to clear that out. I'm going to put that 1, 2 here. Okay, draws it as a point, but you can imagine it as a vector going from 0 to 1, 2. And I'll make all linear combinations of this. So in this case, it's just multiplying it by a constant. But let's look at what happens if I put that constant up to 2. Sure enough, I'm not at 1, 2 anymore, I'm at 2, 4. And so on. I can keep on doing it, I can scale it down. Of course, when I scale it by 0, I'm at the origin. Okay, but if you look, let me just animate this. You look at what's happening when I scale this vector by a constant. Of course, this this constant's just limited between -10 and 10. But you could imagine if it goes through all real numbers, this point is sweeping out a line. You can see it. It's traveling along a line. And if I look at all possible points that it could be, the result is a line. Okay, so when we ask what the span of this is, the answer is that it's a line. It's an entire line that goes through the origin and the point 1, 2. But now let's look at the second one here. Here I've got two vectors, 2, 3 and 1, -1. Let's just start Desmos again and put that there. And was it 1, -1? Yeah. 1, -1. So I've got two vectors there. Again, just imagine that there's an arrow going from here to there, arrow going from here to there. Now I'm going to create all possible linear combinations of these two. Like this. So a linear combination, again, is just a constant times the first vector plus some other constant times the second vector. Okay, very convenient in Desmos. You can see if I add these two together, I get this third vector going from the origin to this black point. Okay, and that's just this very basic linear combination of these two vectors with constants 1. Okay, you can see what happens if I move one of these. Sure enough, I'm going to sweep out a line. If I move the other one, sure enough, I'm going to sweep out a line in the other direction. Now, I'm going to try to animate this, and you have to use your imagination a bit. So that's sweeping out a line, but then the other way it's sweeping out a line. And if it just keeps on bouncing around like that, going through all possible coefficients, you should be able to imagine that it's going to sweep out eventually the entire plane. Okay? It's going to cover every point on the plane eventually if I let a and b be any real number and just vary through all real numbers. Okay? So in this case, when we ask about the span of those 2 points, we would say it's the entire R2. Okay? Great. And I'll leave these as an exercise, which we can talk about when we meet in person. And then we go to our other topic for vector spaces. It's called linear independence. It's a pretty basic concept, but actually, a little difficult to fully understand. So if I have a bunch of vectors, a collection of vectors, we say they're linearly independent if you cannot write one of them as a linear combination of the other ones. All right, so let's see what we mean by that. Here, this is a linearly independent set of vectors because I simply cannot write 1, 0 as a linear combination of 0, 1. Okay? What that might look like is, so I'm trying to write 1, 0 as some linear combination of 0, 1. So I would have to find a constant so that when I multiply this vector by that constant, I would end up at this vector, which you can't do. So the set is linearly independent. And similar to this, you see, I try to write 2, 3 as a linear combination of -1, -1, and I can't do it. If I tried to find such a coefficient, such a constant, it would need to be -2 so that I could get this first component. But when I multiply the second one by -2, I would get 2, so the result would be 2, 2, not 2, 3. So I cannot find such a constant, so then that set is linearly independent. But now if you can write one of the vectors as a linear combination of the other vectors, then that set is called linearly dependent. We're very creative with terminology in mathematics. So here's a set. Before I even talk about dependence, you can see this is a set of 3 vectors in 2-dimensional space. Okay? You notice how in 2 dimensions you only need 2 vectors to determine any point in the space. Right? You could use the vectors 1, 0 and 0, 1, for example, and that can write any other point in the space. So before I even answer this, I know that this needs to be necessarily a linearly dependent set. So one of the vectors in here can be written as a linear combination of the others. And not surprisingly, 2, 3 can be written as 2 times 1, 0 plus 3 times 0, 1. Okay? Considering I can do this, that I can find these numbers, then we say this entire set is linearly dependent. Great. Now, once we have the notions of span and linear dependence, we can talk about dimension. So, I write here that it's the number of vectors in a linearly independent set that spans the space. Okay? Such a set of vectors is called a basis. So a basis is a set of vectors that's linearly independent and spans the entire space. Okay? So that might seem like, again, a complicated notion, but you're very familiar with some bases already. I can draw a set for R2, a set of vectors that will form a basis for R2. There we go. That's one possible basis for R2. How many vectors are there? 2. So then R2 has dimension 2. I'm just thinking while I'm talking. Just want to give you a quick refresher on what I mean by this notation, R2. When I draw my plane, the coordinate axes, each one is a copy of the real numbers. Okay? If I put any point here, that's going to be a real number. So this is a copy of the real numbers, this is a copy of the real numbers. And then we write this plane as the Cartesian product of R and R. And for shorthand, we just write this as R2, like this. Okay? So these are all the familiar spaces that you've worked with in the past. Okay, back to the bases. So this is the one basis for R2, but you could come up with any other basis. You could come up with any set that is linearly independent and spans the entire space. Okay? Something like this, for example. So you can't write one of these vectors in terms of the other one, but you can write any vector in R2 as a combination, a linear combination of these two. Okay, and it's similar for R3. We have our, it's called standard normal basis, the one you all know and love. Just has these 3 unit vectors along the axes, like this. But foreseeably, you could come up with another basis for R3. Now, to find out the dimension of the space, we just have to count the number of vectors in this basis. We've got 3, and so the dimension is 3 for the space. R42, that's 42 copies of real numbers. You could, again, write out a basis. It would be, the standard normal one would be 1, 0, 0, 0, 0, 0, 0, all the way up to 42 entries in that vector. But it works in the same way as these simpler examples. That's my point here. Now you could have a plane in R3. Here's my plane in R3. I live in 3 dimensions. And here's a plane. Okay. It is floating around in space. I want to find a basis for it. Well, I'm just going to physically draw a basis on here. In this case, I'm just going to draw a set of axes like this, and no matter where I put it in space, you can see I can move it around and it remains unchanging. Imagine that it's flat, not that it's curvy. Okay, and so if I hold it out here, that's my plane in R2. Let's say it goes through the origin as well, so the origin's right there. Then I look at how many vectors are there on this plane that will span the whole plane, and are linearly independent. Well, not surprisingly, you need two vectors. So a plane in R3 isn't three-dimensional. The plane itself, if you just restrict yourself to the surface, has dimension 2. So this has dimension 2. It's really just a copy of R2, what's called embedded in R3. So you take that plane, you can move it around in R3, you don't change the dimension of the space. Okay, I have some practice for you. I'll leave you to that and we can talk about it when we meet next.